In this chapter, we'll turn our attention to production. We'll start by examining how we treat how the production of goods works in economic models. We can model production with a function that takes in inputs, here we have capital K and labor L, and transforms them into output. So we let Q be the quantity of the output. Depending on what type of production we're analyzing, we can have different kinds of arguments in this production function representing different types of inputs. But the standard is to use capital and labor. Otherwise, we could think about inputs like land, raw materials, or some intangible ideas like innovation or entrepreneurship. Note here that capital specifically refers to physical assets that aid in production. It does not refer to money. The production function is going to tell us if I specify a certain quantity of capital and a certain quantity of labor, the quantity of output that I'm going to get. If I take the partial derivatives of Q with respect to capital and labor, I get the marginal products of capital and labor. I can write this as just F sub K and F sub L. This is going to tell me how much additional output I can get for each additional unit of input. Just like we have in consumer theory, there's typically diminishing returns in production as well. For each input, the second partial derivative is going to be negative. That means that if I hold capital fixed and just increase labor, or if I hold labor fixed and just increase capital, the amount of additional output I get for each additional input is going to be diminishing. However, it's not enough just to look at these second partial derivatives because we also need to think about the cross partial. So this is the second derivative with respect to capital and labor. Typically, these are going to be positive because we think that having more capital makes workers more productive and vice versa. As economists, we generally like to think about marginal value. So we think about marginal products of capital and labor, but we can also think about average products. So the average product of labor is just going to be the total output divided by the quantity of labor. It's going to be the average amount of output each worker generates. As an example, suppose we have a production function for fly swatters as a function of capital and labor. If capital is fixed at 10, then we just have Q is 60,000 L squared minus 1,000 L cubed. We can then calculate the marginal product. So the marginal product of labor is going to be the first derivative, which is going to be this. As expected, if we write out the second derivative, we can see that the marginal product of labor is indeed going to be diminishing. But a property that this production function has is that past L over 40, the marginal product is actually going to be negative. So adding more workers not only becomes less and less productive, it's actually going to reduce the amount of output that we can generate. So for this production function, the marginal product is going to be this, and the average product is just going to be Q over L, which is going to be this. And one interesting property of average products and marginal products is that the two curves are always going to intersect at the maximum value of the average product. So let's think about why this is. If the marginal product is higher than the average product, that means that each additional unit is pushing the average up, so that the average product should be increasing. If the marginal product is less than the average product, then each additional unit of input is dragging the average down. So it stands to reason then when the marginal product exactly equals the average product, then it's neither increasing nor decreasing, but flat, indicating that we're at a local maximum. In this case, the average product is maximized at L equals 30. And then if we plug in 30 into each of these equations, we get that with 30 units of labor, both the marginal product and the average product are equal to 900,000, which shows that when the marginal product equals the average product is maximized. In consumer theory, we had indifference curves, which showed bundles of goods that each produced the same level of utility. Analogously, in producer theory, we have isoquants, and these are going to be all the bundles of inputs that produce the same quantity of output. So these are going to represent the level curves of the production function. So we're going to let the output be fixed at some Q naught and think of all the different capital and labor combinations that can produce the same quantity. The slope of an isoquant is called the marginal rate of technical substitution. So the marginal rate of technical substitution, if we're doing labor for capital, is going to be minus dk dl evaluated along the isoquant Q equals Q naught. This is going to indicate the rate at which we can trade one input for another while maintaining the output at the same level. This diagram shows a few isoquants plotted at different output levels. As we move down an isoquant, we're reducing the capital input and increasing the labor input, and the curvature indicates that we would likely be best off using a balanced mixture of the two rather than relying heavily on one or the other, similarly to how an indifference curve of the same shape would indicate a preference for variety. If we take the total differential of the production function, so these are going to be our marginal products, and we set this equal to 0 because along an isoquant, the quantity doesn't actually change, and we rearrange this expression, we get that minus dk dl is equal to FL over Fk. So what that means is that the marginal rate of technical substitution is equal to the ratio of the marginal products of labor and capital. Now, this is analogous to how in consumer theory, the marginal rate of substitution was equal to the ratio of marginal utilities. Now, it might be tempting to conclude that as we move down the isoquant, so if we move down the isoquant, the amount of capital we utilize decreases, so the amount of labor we utilize increases. That means with diminishing returns, the marginal product of capital is increasing while the marginal product of labor is decreasing, and so therefore the marginal rate of technical substitution is going to be decreasing, meaning that the slope of the isoquant gets flatter. Now, this isn't necessarily the right way to interpret it, because when we're talking about marginal product, what we're saying is I hold one input fixed and I just change the other one. When we're moving up and down an isoquant, that's not what we're doing. We're changing both inputs at the same time because one is being substituted for the other one. If we want to rigorously show that the marginal rate of technical substitution is decreasing, we need to show that dRTS dL is less than 0. So RTS is FL over Fk. So to find dRTS dL, we're doing ddL of this thing. So we need to use the quotient rule. Now, if we use the quotient rule, in the denominator, we're just going to have fk squared. What do we have in the numerator? So the first term is going to be fk times the derivative of fl with respect to L. So we're going to have FLL, but changing the amount of labor as we move down isoquant is also going to change the amount of capital, which in turn is going to affect the marginal product of labor. So we have FLL plus FLK times DK DL. Then the second term of this is going to be FL times FKL plus FKK times DK DL. Now we can use the implicit function theorem and substitute minus FL over FK for DK DL. So if we substitute for here, we're just going to put fk cubed in the denominator, and we're going to multiply all the terms that don't have dk dl by fk, and the ones that do by minus fl. So we're going to have fk squared fll minus 2 times fk fl times the cross partial. Remember that the order of differentiation doesn't matter here. And then we're going to have plus fl squared fkk. We assumed that the marginal products were positive. So the first derivatives are positive, but they're diminishing. So the second derivatives, the second partials are negative. So here, the denominator is going to be positive. For this term, fk is positive, fll is negative. This term is negative. This term, likewise, is negative. Fk and fl are positive. So for this entire thing to be negative, we need the cross partial fkl to be positive. So what does this mean? If fkl is positive, that means having more of one input will increase the productivity of the other one. And if that's the case, the producer is better off using a mixture of capital and labor rather than leaning too heavily in one or the other. If we look at our example from before, then the marginal products are going to be like this. So in order for both of these to be positive, we need k times L to be less than 400, or else the second term is going to outgrow the first one. If we write out the second partials, we want these to both be negative. And in this case, we need k times L to be greater than 200, so that both of these expressions will be negative and we have diminishing returns. And finally, we have the cross partial, and we get the same answer regardless of the order of differentiation. And we want this thing to also be positive, which means that we need k times L to be less than 266, which is a stronger condition than this one. So in order to ensure that we have a diminishing marginal rate of technical substitution, k times L has to be between 200 and 266. Now let's think about what happens when, rather than increasing one input at a time, we increase all of them at the same time. So what we're doing here is we're increasing the scale of our production. So on one hand, if we're producing at a larger scale, this might allow us to allocate our inputs more efficiently. But on the other hand, it can also introduce overhead costs that are going to reduce productivity overall. So if I multiply all of my inputs by the same constant t, I want to think about how much this multiply my output by. If output gets multiplied by exactly t as well, then I have constant returns to scale. So that means doubling all the inputs means doubling the amount of outputs. If my output is increased by less than this factor, then I have decreasing returns to scale. This means that I'm kind of hitting a wall past a certain point. And if output is multiplied by more than a factor of t, that means I have increasing returns to scale, which means that I'm producing relatively more as I scale up my production. When we're talking about returns to scale, what we're talking about is a local property. So a production function can have increasing returns to scale at some input levels and decreasing returns to scale at other levels. If a production function is constant returns to scale, then it's going to be homogeneous of degree 1. What that means is that its marginal products are going to be homogeneous of degree 0. So if I multiply capital and labor by the same constant, the marginal product of capital will stay the same, and the marginal product of labor will also stay the same. If the marginal products are homogeneous of degree 0, so scaling up the inputs by the same factor doesn't change the marginal products, then what I can do is let t equals 1 over L. So that means that the marginal product of capital or labor depends only on the ratio rather than the absolute amount. So if I have a production function that is constant returns to scale, then the marginal products only are going to depend on the capital to labor ratio rather than the absolute levels. This graph shows what the isoquants of a constant returns to scale production function will look like. The dotted line shows a ray along which the capital labor ratio remains constant, and therefore the marginal products are constant, and therefore the marginal rate of technical substitution is constant, so that the tangent line is the same slope at each point. This ray is also known as an expansion path, and the fact that it's a straight line here indicates that a company can scale up its production simply by maintaining the same capital labor ratio and scaling everything up proportionally. A production function where the rate of technical substitution depends only on the capital labor ratio is called homothetic, and that's going to give us the property of these straight line expansion paths, which is nice. Now, a constant returns to scale production function will have this property. But so will any transformation of one. So let's let big F be the production function raised to the power gamma. If we apply the chain rule, we see that these terms are just going to cancel out. So the marginal rate of technical substitution of big F is the same as for little f, which means that if little f is homothetic, then big F will be also. However, if we have gamma greater than 1, then if I multiply the inputs by T, I'm going to end up multiplying the outputs not by T, but by T to the gamma. So if gamma is greater than 1, big F is going to be increasing returns to scale. But if I do this transformation, big F is still going to be homothetic, meaning a constant returns to scale production function will be homothetic, but a homothetic production function doesn't necessarily need to be constant returns to scale. It's still going to have that property of linear expansion paths, even though it's increasing returns to scale. More generally, we can write a production function taking any number of input goods, x1 through xn, and it's going to be homogeneous of degree k if scaling up all of those inputs by a factor of t is going to multiply the output by a factor of t to the k. So if k is equal to 1, we have constant returns to scale. If k is less than 1, we have decreasing returns to scale. And if k is greater than 1, we have increasing returns to scale. Recall that when we were going over consumer theory, we talked about constant elasticity of substitution utility functions, but we didn't actually define what elasticity of substitution was. So here we're going to define it. We're going to define the elasticity of substitution as being the proportional change in capital labor ratio over the proportional change in the marginal rate of technical substitution. So what that means is that it's going to tell us the extent to which a producer's input mix is going to change in response to external shocks that cause it to move to a different point on the isoquant where the marginal rate of technical substitution will be different. So if we write this out, we get d log of k over L over d log of FL over FK. So make sure to note that the ratios are flipped here. So labor is in the denominator up here, but in the numerator down here. This is because we would expect, as we increase the marginal rate of technical substitution, so we have a steeper slope, this is because if we increase the marginal rate of technical substitution, that means the slope of the isoquant is going to be steeper, so we're kind of moving up the curve. Then we're going to be moving to a higher capital labor ratio. So we want this whole thing to be positive, which is why the positions of K and L are flipped going from here to here. If the elasticity is high, then a small change in the marginal rate of technical substitution is going to lead to a large change in the capital labor ratio, which means that the isoquant should have a relatively flat shape, whereas if sigma is low, then a large change in the marginal rate of technical substitution leads to only a small change in the capital labor ratio. So the isoquant is going to have a more sharply curved shape. If I have a production function with n inputs, then I can define the elasticity of substitution between any two of them, I and j, as being the proportional change in the ratio, so the ratio of input I over input j, divided by the proportional change in the marginal rate of technical substitution, which is going to equal the marginal product of j over the marginal product of I. So once again, pay attention. The position of I is flipped from here to here. This diagram helps to visualize this concept of elasticity of substitution. The marginal rate of technical substitution is the slope of the tangent line, while the capital labor ratio is the slope of the line from the origin to where the input bundle is. And so the elasticity of substitution says, how far do we have to move along the isoquant for a given change in the slope of the tangent line? So it's going to measure how sharply curved the isoquant is. Just like with utility functions, we can look at a few special cases. If we have a linear production function like this, the isoquants are just going to be straight lines, and the marginal rate of technical substitution is just going to be a constant, beta over alpha. This means that if we're computing the elasticity of substitution, well, because the marginal rate of technical substitution never changes, the elasticity of substitution is infinite. This would describe a production process where the inputs, capital and labor, can be freely substituted for each other. So the producer can just use whichever one is more cost effective exclusively. There's no benefits to using a mixture of the inputs. If we have a fixed proportions production function, so the output is equal to the minimum of alpha, k, and beta times L. This describes a production process where the inputs always have to be used in the same ratio. Any amount of additional k or additional L by itself is not going to give me any additional output. Because the capital labor ratio always has to remain constant, that means that the elasticity of substitution is equal to 0 because the numerator can never change. We also, of course, have our old friend Cobb-Douglas, and we can see the usefulness of this functional form because this production function is going to be homogeneous of degree alpha plus beta. If I multiply the inputs by t, that's going to multiply the outputs by t to the alpha plus beta. So what that means is if alpha plus beta equals 1, we're going to have constant returns to scale. Greater than 1 will have increasing returns to scale, and less than 1 will have decreasing returns to scale. Just like with utility functions, this can be easier to analyze if we take a logarithmic transformation like so. But we have to be careful here because unlike with utility, the left-hand side actually represents something tangible, right? The left-hand side here represents the quantity of output and not just some subjective measure of utility. So we can't just go transforming it arbitrarily. The coefficients alpha and beta are going to represent the elasticities of output with respect to capital and labor. So if I increase the amount of capital by 1%, I'm going to increase the amount of output by alpha percent. If I increase the amount of labor by 1%, I'm going to increase the output by beta percent. Finally, we have the CES production function, which is going to take the form k to the rho plus L to the rho all to the gamma over rho. And the elasticity of substitution is going to depend on rho. It's going to be 1 over 1 minus rho. Gamma is going to indicate the returns to scale. We're going to have constant if gamma is equal to 1, increasing if gamma is greater than 1, and decreasing if gamma is less than 1. If we change the coefficient rho, we can get all the different cases that we just talked about. So if rho is equal to 1, then we're going to have a linear production function. If we let rho be equal to minus infinity, then we're going to get fixed proportions. And if we let rho equals 0, then we're going to get Cobb-Douglas. So just like in consumer theory, the CES functional form encapsulates all of these different cases. We just have to vary the parameter rho. This diagram shows all of these cases graphically. With linear production functions, the isoquants are straight lines, so that the marginal rate of technical substitution is fixed at beta over alpha, and the optimal input bundle is likely going to be at one of the corners. With fixed proportions, the marginal rate of technical substitution is undefined, since the optimal input bundle is always going to be at one of the corners, and therefore a long array from the origin with a capital labor ratio equal to beta over alpha. With Cobb-Douglas, or with any other intermediate function, we get the usual curved isoquants. One example of a CES production function is what's called the generalized Leontief production function. So we're going to let rho equals 1/2 and gamma equals 1, which means that Q is equal to K plus L plus 2 times the square root of K times L. If we compute the marginal products, we're going to get this for the marginal product of capital and this for the marginal product of labor. And so the marginal rate of technical substitution is going to be this. And the elasticity of substitution is going to be constant. It's going to be 1 over 1 minus rho. Rho is 1/2. So the elasticity of substitution is going to be 2. So we can see here that the marginal rate of technical substitution is just a function of the capital labor ratio. And a 1% change in the marginal rate of technical substitution gives us a 2% change in the capital labor ratio. Production technologies are rarely just going to be static and are generally going to improve over time as we have improved techniques. So we can either produce the same output with less inputs or use the same inputs to produce more output. This is going to cause the isoquant to shift inward, which is a little bit counterintuitive, but if you think about it, that just means that I can produce the same amount using less inputs, so the capital labor bundles that are used to produce the same level Q are going to be further in. We can account for this in our production function by having this term AT, which represents technical progress over time. So this is going to represent all of the influences that go into determining Q aside from the input levels. This diagram shows how a technical improvement is going to shift the isoquant inwards from IQ prime to IQ double prime. The same level of output can now be produced with less capital at the same level of labor or less labor at the same level of capital. If we now allow both the technology level and the inputs to change over time, we can really decompose the growth rate of the output level. So we have Q is equal to AF, which means that Q prime is equal to A prime F plus F prime A, for A prime over A times Q plus Q over F, and then F prime we write as Fk times K prime plus Fl times L prime. If we divide through by Q, we get that Q prime over Q is equal to A prime over A plus Fk times K over F, K prime over K, plus Fl times L over F, L prime over L. Now what we can do is we can let the growth rate of any variable just be its derivative divided by its value. That means that the growth rate of Q is equal to the growth rate of A plus Fk, K over F times the growth rate of K plus Fl, L over F times the growth rate of L. If we take a look at these two terms, Fk is df dk times K over F. So this is going to be the output elasticity of capital. And this correspondingly is going to be the output elasticity of labor. So what that means is that the growth rate of output is going to equal the growth rate of technical progress plus the growth rate of the capital stock times the output elasticity of capital plus the growth rate of the labor force times the output elasticity of labor. If we have a Cobb-Douglas production function with constant returns to scale, so we're going to have that beta is 1 minus alpha, and a constant growth rate in technology, so technology improves at a rate equal to theta, then what we're going to get is that the growth rate of output is equal to the growth rate of technology, which is just theta, plus alpha times the growth rate of capital, plus 1 minus alpha times the growth rate of labor. Now that we have some idea of how production functions work, in the next chapter, we'll continue our discussion of producer theory by incorporating costs and thinking about the producer's optimization process.